Hello viewers, under vector calculus we have a question that we are going to solve under directional derivative. And so in the question we have that the temperature distribution in space is given as T into x, y, z equal to xy plus exponent minus z squared sine into x, y. And then we are asked to find the rate of change of the temperature at the point. We are given this point in the direction of the vector. This is the direction of the vector. And then the second part of the question is to determine if the temperature is increasing or decreasing. So this is a typical question on the directional derivative. So we are going to be solving it. So it's a solution. So in this solution, we are going to write out our question. So our question is phi t into x, y, z equal to xy plus exponent minus z squared sine into xy. So that is the question. So we know that in solving directional derivative, we have to, introduce the formula for solving directional derivative. So I can say let directional derivative be, let's denote it with let's use this symbol dd, directional derivative. Let's use dd to denote our directional derivative. So we can now say that a directional derivative dd, the formula will be equal to the operator of the temperature multiplied by the unit vector of B. But if we say that the unit vector of B equal to this over the magnitude of B, then over the magnitude of B, then a directional derivative will be given by the formula the operator of the temperature multiplying this all over. So this is the formula for calculating the directional derivative of a vector. And so we are going to have, this is the operator of the temperature, because since we are considering temperature, that's why we're having the operator of the temperature. And so the operator means we are going to be differentiating partially with respect to the different axes, that is x, y, and z. So our operator of the temperature, this is what the formula will look like. We are going to have partial derivative of t with respect to x in the I direction plus partial derivative of t with respect to y in the j direction plus partial derivative of t with respect to z in the k direction. So because we are considering temperature, that's why we are taking partial derivative with respect to of t with respect to different, assuming it was maybe phi here or theta, it would have been theta divided by this. So we are going to be finding the partial derivative of t with respect to x, and then t with respect to y, and then again t with respect to z. And so when we are done with that, we find the unit vector of b, we multiply our answer, and then we come out with the final answer. So our partial derivative of t with respect to x will be, now if we are differentiating using this equation, if we are differentiating t with respect to x in this equation partially, this is partial differentiation, so we are differentiating t with respect to x using this equation. So when we, there's x here, so when we differentiate t with respect to x partially, at this point we are going to have our y plus, and now we have this here, so we know that we have exponent minus z squared sine into xy. So when we are differentiating the all of this with respect to x, we are going to have this. Let me give you a brief solution, because this is where our xy is concentrated, and we are differentiating with respect to x. So we are going to be having something like this. So if we say at this point, let u equal to xy, it means at this point our sign, okay, if u is equal to xy and we say and y is equal to, if we make y to be equal to sine xy, sine into xy, and we say that our u is equal to xy, it means our y here will be equal to sine u. So if we differentiate u with respect to x here, so du with respect to x here, we are going to, if we differentiate u with respect to x here, since we are dealing with x, we are going to have y, and then if we differentiate y with respect to u here, if we differentiate y with respect to u in this other equation, we are going to have cos u. And so when we now apply our chain rule that dy dx will be equal to du, this is du over dx times dy over du. So this will give us y cos u. And so since we have this to be y cos u, this will now give us, but u is xy, so we have y cos into xy. So when we are differentiating the all of this with respect to x, because it's change in temperature, we are going to have, because this is y cos xy, now multiplying this one will give us exponent minus z squared dot y cos into xy. And so if we want to further this will be y plus this y, we can, when we multiply this, we can have it to be y plus y cos into xy exponent minus z square. So if we differentiate t with respect to x for this equation, this is what we are going to have. And so we've been given initial condition. The initial condition is that at the point 0, 1 and minus 1, so this means that x equal to 0, y equal to 1 and z equal to minus 1. And so because we have that, we can now bring in those values here. So we are going to have, of course, if I can factorize this, okay, let's just do it. Y is 1, so I write 1 here. This y is 1 plus another y is 1 cos xy, x is 0 times y is 1, and then we have exponent minus z is what? Minus 1, so we have minus 1 all raised to power 2. So that is what we have there. So we continue our solution from here. We continue our solution so that we are going to have, from here, we have 1 plus cos 0. Cos 0, what is cos 0 going to give us? We have cos 0 is 1, because we have 1 plus 1 times cos 0 times 1 is 0. So we have times 1 times exponent minus 1 into minus. So minus 1 all squared is 1. So exponent, what is our exponent? Minus 1. Exponent minus 1 gives us, so this one will be times exponent minus 1. Okay, so our answer will be 1 plus 1 times 1 is 1 times exponent minus 1, so exponent minus 1. So that is the value of what we are going to have in our differentiation of when we differentiate. That's the value we have when we differentiate y, when we differentiate t with respect to x partially. So we are done with that. So the next one is to differentiate t with respect to y using the same equation, differentiate t with respect to y using the same equation. So when we do that, I'm not going to go through the process again. I've shown you how to do it. So when we are differentiating t with respect to y using this equation, so partially, so this one, the first, we have xy here, so we are going to have differentiating with respect to y, we have x plus. So when we now differentiate this with respect to y using this same method, we are going to have exponent minus z squared dot x cos into xy. That's what we are going to have when we differentiate it with respect to y. So this will be the same thing as saying this will be equal to, okay, let's say this is equal to, this will be, if we multiply this by this, so we can have x plus, we take this one, x cos into xy exponent minus z square. Okay, that's what we have there. And remember that we have initial condition where we are given that x is equal to 0, y is equal to 1, and z is equal to minus 1. So that will give us 1, x is 1, okay, x is 0 here, plus x is another 0 here, this x, cos into x is 0 times 1, exponent minus z is minus 1 raised to power 2. So when we work out the all of this, is going to give us 0. And so we are done with that. So we can now take change in t over change in z. So still using this equation to differentiate it partially. So if we see here xy, so there's no z, so we leave it. So we are going to differentiate only this part of the equation because there's no z. So here will be 0 plus. So we differentiate this part. So this is an exponential This is an exponent. And so if we are to differentiate this with respect to z, it's going to give us minus 2z exponent minus z square sine into xy. Okay, that's how to differentiate that. And so with our initial condition of x equal to 0, y equal to 1, and z equal to minus 1, we are going to have minus 2 into z is minus 1, exponent minus into z is minus 1 all squared, sine into 0 times 1. Okay, and so when we solve this out, we are going to have that this will give us 0 again. So what do we have? It means that our operator of temperature, which is equal to this formula, our operator of temperature, which is equal to this formula here, dt over dx I plus dt over dyj plus dt over dz k. Okay, so now that we've got in here, we know that our dt over dx is what? This is the value. Our dt over dx, this is the value of our dt. This is the value of our dt over dx. This is the value. So we have 1 plus exponent minus 1 I plus. We know that our value of dt over dy is 0. So we have 0j plus that over dz, dt over dz is 0. So we have 0k. So this is for our operator of the temperature. So now we need to find the unit vector of B. The unit vector of B. So the unit vector of B is equal to B all over the magnitude. Vector B all over the magnitude of B. Of course, we know that vector B from our question, is I plus 2j minus k. Vector B from our question is I plus 2j. So we have I plus 2j minus k divided by the magnitude of B will be 1 all squared plus 2 all squared plus into minus 1 all squared. So this is going to give us I plus 2j minus k all over root 1 plus 2, 1 square is 1 plus 2 square is 4 plus minus 1 square is 1. So this, of course, will give us I plus 2j minus k divided by 1 plus 4 is 5 plus 1 root 6. So we have that the unit vector of B is I plus 2j minus k all over root 6. So that's what we have there. So this means that we can now bring in the formula for our directional derivative, which is, we represented it using this, equal to the operator of the temperature times the value of the unit vector of B. And so if we have to express this mathematically, this is going to be the value for our operator. The value of our operator is this. So we are going to have 1 plus exponent minus 1 I plus 0 j plus 0 k, and is multiplying. Note the multiplication is dot product, the unit vector of b, so this is I plus 2j minus k divided by root 6. Okay, so we can do it here. Now, I is going to be multiplying I, j is going to be multiplying j, and k is going to be multiplying k. So if I, the all of I is multiplying this, of course, you know I times I is 1. The dot product of I and I is 1, so I times I is 1. So this 1 plus exponent minus 1 multiplying 1 will give us 1 plus exponent minus 1. And then we know that 0 times 2 is 0 for the j. 0 times 2 here is 0 for the j. 0 times k here is also 0. So everything will be divided by 6, because here in the numerator we have 1. So 1 times root 6 will give us root 6 rather. So this is divided by root 6. So we can now use our calculator to find 1 plus. Let's find the value of exponent minus 1. Exponent minus 1. The value of exponent minus 1 is 0.3678. So we divide it by root 6. Okay. So, but we divide it by root 6. So let's find the final answer. So we have 1 plus 0.3678 divided by root 6. And that gives us 0.5584. Okay. And so in this question now, we've gotten to almost the end of this question, and we've been able, this is the directional, this is the answer for the directional derivative of vector b. And this one, the second part of the question, was for us to determine, is the temperature increasing or decreasing? So at this point, since the answer we have from the temperature is positive, we can say that the temperature is decreasing. Since the answer we have for the temperature is positive, we can say that the temperature is increasing rather. Since the answer is positive, the temperature is increasing. So assuming we had a negative answer here, we would have said that the temperature is decreasing. So viewers, basically, this is how to go about solving a problem on directional derivative. This is the solution to that problem. So we have, this is the continuation to the end of the problem. Again, this is the first part. And this is the second part and the final solution. Thank you.